need to talk about the next application, which is going to be molar volume. And the molar volume is the volume per mole. So how many liters per mole does the gas occupy? And so there are molar volumes that people memorize. For example, STP. You know, I've had this molar volume memorized since I took Chem in high school. 22.4 liters per mole. And so under STP, this is the US, you know, with 1 atmosphere. STP. Or 22.7 liters per mole, if we're talking about bar, 1 bar. Both of these numbers I found pretty useless. Why? Both of these numbers I found pretty useless because nobody really works at 0 degrees C. So what about room temperature and room pressure? What is room temperature and room pressure? Well, the molar volume at room temperature and pressure, this is pretty useful. No, it's 24.5 liters per mole. If I'm doing pressure of 1 atmosphere. So this would be a US kind of thing. And so what happens is that when it's colder, the gases contract. When it's warmer, the gases expand. So it expands about 2 liters. You can go from 0, freezing, to room temperature. This is room temperature and pressure in the US, but you know, in Europe or wherever else, we're dealing with 1 bar. And this is going to be 24.8 liters per mole. And so these two are going to be much more useful numbers to remember. So, well, we don't have to remember any of these because we can calculate it. You know, so if we ever forget, we can just go ahead and calculate the molar volume. But you know, they're pretty handy. I mean, this one is quite useful. But we can calculate it using the definition of molar volume. Molar volume is the volume per mole. And so N, what is N equal to? N is equal to PV over RT. And so we'll substitute that in here. So we'll get volume over PV over RT. And then we'll invert and multiply. The volumes cancel, and that just gives us RT over P. And so it's really pretty easy to calculate the molar volume at any temperature and pressure. At any temperature and pressure. And so both of these are 25 degrees C, or 298 Kelvin. Compare the molar volumes of helium and neon at 30 degrees C and 1.10 torr. And so what we have to do is 30 degrees C, we have to convert that into Kelvin. 1.10 torr, we have to convert that into atmospheres. And then we'll just plug that in. R, we know that that is temperature and pressure. Plug that in with the right units, or convert the units in the equation. And then we get this. Molar volume is RT over P. Calculate it. We get 1.72 times 10 to the 4th liters per mole. It's huge. It's 17,200 liters per mole. Why so huge? 17,000 liters per mole? It's because the pressure is so low. And the pressure is only 1 torr. There's 760 torr in an atmosphere. The pressure is very low, then the gas can expand. High pressure, the gases get compressed. Low pressure, the gases expand. And the molar volume doesn't depend on what the gas is. So, you know, the molar volume of any gas is going to be given by this equation. So we don't need to know what the gas is. We just need to know how many moles. What is the molar volume of carbon dioxide gas at a pressure of 0.974 atmospheres and temperature of 43 degrees C? And so we just have to convert that into Kelvin. And so the pressure is 0.974 atmospheres, which is slightly less than 1 atmosphere. And the temperature is kind of high at 43, so 43 degrees C, which is plus 273, which would be 316 Kelvin. So the molar volume is equal to R, 0.08206 liters times atmosphere per mole Kelvin, times T, 316 Kelvin, divided by P, 0.974 atmospheres. So atmospheres cancel, Kelvins cancel, that leaves us with liters per mole. So let's figure out what it is. .08206 times 316 divided by 0.974. Oops. 26.6. 26.62 liters per mole. And so what happens is the gases expand with increasing temperature. Gases expand with decreasing pressure. Gases contract with decreasing temperature, and gases contract with increasing pressure. And so the pressure and temperature is going to affect the volume of the gas. So we've got 26.6 liters here. Okay, this is another molar volume. This is using molar volume. Actually, this is how we're going to use molar volume. We're going to use molar volume in stoichiometry. Like, let's take a look at this first problem here. One small-scale laboratory method for preparing oxygen is to heat potassium chlorate in the presence of a catalyst. 2 key CO3s